Hello everyone, welcome to this lecture. I am Amlan Das. Today I will discuss about Stern-Gerlach experiment. Okay. This experiment first performed in 1921 by O. Stern and W. Gerlach, aimed at verifying the essential features of the vector atom model, that is, the existence of the electron spin and space quantization of the angular momentum vectors due to both orbital and spin motion of the electron in an atom. Okay. Now, the experiment has been performed originally by using a beam of neutral silver atom and was later repeated with the beam of neutral atom of other elements like zinc, cadmium, mercury, lead, etc. Okay. Now we discuss about the experimental setup of Stern-Gerlach experiment. Okay. Now this is a sketch of apparatus of the experimental setup of Stern-Gerlach experiment. Okay. Now this is an electric oven. Okay. This is an electric oven. Now a sample silver is heated in this oven. Okay. A sample silver is heated in this oven and it produces rays of silver atoms. Now these silver atoms comes out through a narrow slit S. Now these rays are passing through two parallelly aligned slit S1 and S2 and emerges as a thin ribbon shaped beam of atoms. Now these rays are passing through two pole pieces of an electromagnet and they finally strike a photographic plate P. Okay. Now the pole pieces are of the special shape. One of the pole pieces is of the form of a knife edge with the edge in the direction of motion of the silver atom, and the other pole pieces has a channel cut parallel to this edge. Okay. Now the pole pieces are of this special shape to produce inhomogeneous magnetic field. Okay. Now the entire arrangement is enclosed in an evacuated chamber to enable the silver atom to traverse the field without collision. Okay. Now when there is no magnetic field, atomic beam travels undeflected towards the plate P. That is, before the application of the magnetic field, the beam of the silver atom are observed to produce a linear trace on the photographic plate. Okay. If we draw this, then we will get this type of pattern. Okay. That is, before the application of the magnetic field, the silver atoms produce a linear trace on the photographic plate. Okay. Now, after the application of the magnetic field, each silver atom is acted upon by a translational force, and so they produce a double trace on the photographic plate. Okay. If we draw this, then we will get this type of pattern. Okay. So before the application of the magnetic field, the silver atom produces a linear trace on the photographic plate, and after application of the magnetic field, the silver atom, the beam of the silver atom are produced double trace on the photographic plate. Okay. Now, these two linear traces are converging at the two ends. Okay. Now, the silver atoms in the beam, each having magnetic dipole moment mu, traveling with the same velocity v0 when they enter into a non-homogeneous magnetic field B. They are acted upon by the force F is equals to mu dot grad into B. Okay. When each silver atom of magnetic dipole moment mu traveling with the same velocity v0 enter into a non-homogeneous magnetic field B, they are acted upon by the force F is equals to mu dot grad into B. Okay. Now, we refer to the coordinate system having x axis in the direction of motion of the silver atom and z axis in the direction of B. Okay. We refer to the coordinate system having x axis in the direction of the silver atom and the y axis in the direction of z axis in the direction of B. Okay. So, magnetic field acts in z direction. Now, since magnetic field B acts only in z direction, so the magnetic field has gradient only in z direction. So, we may write del B del x equals to 0 and del B del y equals to 0, since magnetic field has gradient only in z direction. Okay. Now, this equation can be written as F equals to mu x del del x plus mu y del del y plus mu z del del z, and since B has only z component, so we may write B into z cap. Okay. So, this can be written as this is equals to simply mu z into del B del z into z cap, since del B del x equals to 0 and del B del y equals to 0. So, we can write F equals to this. Okay. So, this is the force acting on the silver atom. Now, due to this force, each silver atom of mass m, while moving through the magnetic field, has an acceleration in the z direction given by Az equals to F by m. Okay. Due to this force, each silver atom of mass m, while moving through the magnetic field, has an acceleration is this. Now, if we put the value of F from this equation, then we get this is equals to mu z into 1 by m into del B del z. Okay. So, this is the acceleration. Okay. Now, the velocity component of the atom in the x direction is v0 and in the y direction is 0. Okay. Velocity component of the atom in x direction is v0 and y direction is 0. So, each atom passes through the magnetic field in the time interval t equals to, we know that time is equals to distance by velocity. So, here distance is L. So, L by velocity is v0. Okay. So each silver atom passes through the magnetic field in the time interval t equals to L by V0. Okay. Now here small l is extension of the magnetic field in the x direction. Okay. L is extension of the magnetic field in the x direction. So this is the acceleration and this is the time. Now when an atom comes out from the magnetic field, it has been displaced in the z direction by this distance. Suppose this is delta z dashed. Okay. When a silver atom comes out from the magnetic field, it has been displaced in the z direction by delta z dashed. Okay. So delta z dashed is equals to, we know that this is equals to half into acceleration az into t square time square. From classical mechanics we know that this is equals to half acceleration into time square. Okay. Now if we put the value of az and t from this equation, then we get this is equals to half, and value of az is this, that is mu z to 1 by m into del b del z, and the value of t is L square by V0 square. So this is equals to L square by V0 square. Okay. So this can be written as this is equals to half mu z by m into del b del z into L square by V0 square. Okay. So this is the displacement in the x direction. Okay. When an atom comes out from the magnetic field. Now on emerging from the magnetic field, when the atom reaches the photographic plate P, the total displacement in the z direction suffered by the silver atom is this. Okay. Suppose this is delta z. When the silver atom reaches the photographic plate P, total displacement in the z direction is delta z. Okay. So total displacement is delta z. Now let us calculate delta z. Now to calculate delta z, let us draw this portion. Okay. We draw this portion. Suppose this is A, this is B, and this is C, and this point is D, and this point is E. Okay. Now here this portion is small l, that is extension of the magnetic field in the x direction, and suppose this is capital L. Okay. This distance is capital L, that is distance of the photographic plate from the near end of the magnetic field. Okay. So this is small l, this is capital L, this is delta z, and this is delta z dashed. Okay. Now here if we draw here, then this is delta z, this is delta z dashed, this is capital L, and this is small l. Okay. Now from the triangle ABC and the triangle ADE, we get from the triangle ABC and the triangle ADE, we get this side by this side is equals to this side by this side, that is BC by DE. BC by DE is equals to AB by AD is equals to AB by AD. Now if we put the value of BC, DE, AB and AD, then we get, or BC is equals to delta Z. So delta Z by DE is equals to delta Z dash. So delta Z dash is equals to AB is this plus this, that is small l plus capital L. Small l plus capital L, and AD is small l. So we may write delta Z equals to delta Z dash into 1 plus capital L by small l. Okay. So this is delta Z. Now if we put the value of delta Z dash from this equation, then we get this is equals to half mu Z by m into L square by V0 square to 1 plus L by L into del B del Z. Okay. So this is delta Z. Okay. Now that is delta Z means total displacement in the Z direction suffered by the silver atom on the photographic plate P. Okay. Now from vector atom model we know that the magnetic dipole moment of an electron in an atom mu Z is equals to minus G mj into mu B. Okay. From vector atom model we know that the magnetic dipole moment of an electron in an atom is minus G mj into mu B, where mj is the magnetic quantum number, total magnetic quantum number of the electron in an atom, and mu B, we know that mu B is equals to EH by 4 pi me. Okay. Here H is Planck's constant and me is the mass of the electron. Mu B is called Bohr magneton. Okay. So mu B, we know that mu B is called Bohr magneton, and G, we know that G is 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 by 2 J into J plus 1. G is called Landé-G factor or splitting factor. Okay. G is called Landé-G factor. Landé-G factor or splitting factor. Now, if we put the value of mu Z in this equation, then we get delta Z is equals to half, and value of mu Z is minus G mj mu B by m into L square by V0 square into 1 plus L by L into del B del Z. Del B del Z. Okay. So this is delta Z. Okay. Now the original experiment was done with the silver atom, for which normal state is 2s half. Okay. Original experiment was done with the silver atom, for which normal state is 2s half. Now for S state, value of L is, we know that L equals to 0. For S state, L equals to 0, and here J is half and S equals to half. Okay. Here L is total orbital angular momentum quantum number, and S is total spin angular momentum quantum number, and J is total angular momentum quantum number of the electron. Okay. Now, if we put the value of L equals to 0, J equals to 0 and S equals to 0 in this equation, then the value of G becomes G is equals to 1 plus value of J is half into half plus 1 plus S is half into half plus 1 minus value of L is 0, so 0 into 0 plus 1 by value of J is half into half plus 1. Okay. Now, this is equals to 1 plus half into 3 by 2 plus half into 3 by 2 by 3 by 2. So, this is equals to 1 plus 3 by 4 this is equals to 1 plus 3 by 4 plus 3 by 4 by 3 by 2. So, this is equals to 1 plus 6 by 4 by 3 by 2, that is 1 plus 1 equals to 2. Okay. So, the value of Landis factor G equals to 2. Okay. So, we get here G equals to 2 and Mj is plus minus half. Okay. Now, if we put the value of G equals to 2 and Mj equals to plus minus half in this equation, then we get delta Z is equals to minus half into value of G is 2 into plus minus half into mu V by m V0 square into L square 1 plus L by L into del B del Z. Okay. So, this is equals to plus minus mu B by m V0 square into L square 1 plus L by L into del B del Z. Okay. Suppose this is equation 1. So, this is delta Z and this is delta Z. Okay. Now, so what is delta Z? Total displacement in the Z direction on the photographic plate by the silver atoms. Okay. Now, when there is no magnetic field, silver atoms should produce on the photographic plate this type of pattern. Okay. When there is no magnetic field, atomic beam are produced on the photographic plate this type of linear trace, and after application of the magnetic field, the silver atom produce on the photographic plate two linear trace. Okay. If we draw this, we will get this type of pattern. So, this is the linear trace produced by the silver atom on the photographic plate before application of the magnetic field, and these are the two linear traces produced by the silver atom on the photographic plate after application of the magnetic field. Now, this equation 1 shows that for the two values of delta Z. So, delta Z, what is delta Z? This is delta Z, this is delta Z. Separation is delta Z. So, equation 1 shows that corresponding to two values of delta Z in presence of magnetic field, the silver atom should produce two linear traces placed symmetrically situated on the either side of the trace produced before the application of the magnetic field. Okay. Equation 1 shows that for the two values of delta Z in presence of magnetic field, silver atom should produce two linear traces placed symmetrically on the either side of the trace produced before application of the magnetic field. Okay. Now, in actual practice, the field gradient del B del Z decreases both in positive and negative direction to become 0 beyond a distance. Okay. In actual practice, del B del Z decreases both in positive and negative direction to become 0 beyond a distance. For this reason, the two linear traces converges at the two ends. Okay. And if we draw this, then we will get this type of pattern. If we draw this, then we will get this type of pattern. So, here we see that two linear traces converges at the two ends. Okay. Now, by measuring del B del Z, and if we take V0 to be the most probable velocity, that is V0 equals to root over 2 kt by m, and measuring delta Z, value of the magnetic dipole moment mu b is calculated from equation 1. Okay. If we measure del B del Z, if we measure delta Z, and if we take V0 to be the most probable velocity, that is root over 2 kt by m, from equation 1 we can calculate the value of magnetic dipole moment mu b. Okay. Now, this experimentally determined value of mu b is found to agree well with the theoretical value. Okay. Thus, this experiment confirms the vector atom model. Thus, we discuss the Stern Gerlach experiment. Okay. Thank you for watching this video.